How was the weekend?
Was good. It was very cold Saturday.
Yeah.
Wasn't ready for that. So I just told myself, oh, I should get a wool or something. I came outside and it was tiring.
Yeah. Well, my wife and I, we were determined to see the CN Tower.
Yeah.
We we ended up well walking at least half the way. It was really cold. But that was fun. Okay. Welcome back. Let's see. I'm going to start with a remark I should have made about Sadinger's result. So I'm hopping back. Okay, so the result we proved requires stability of point spectrum. Sorry, of point spectrum. But I neglected to mention this. In this case, for scalar second order, we can use a Sturm-Liouville theory, a variation on that. A variation in that it's on the whole line and not on the bounded interval as usual. And we can apply a principal eigenfunction result, which is basically that if we have point spectrum, which is the largest eigenvalue, the eigenfunction must be of one sign. So it might be that it could be that the essential spectrum is the largest spectrum, and all the other point spectra would be somehow embedded in that. In that case, it doesn't say anything, but if it's outside, one can show that it must have one sign. It's if and only if. Okay, so we want the zero eigen. Oh, and it's simple. So the zero eigenfunction, so the eigenfunction at lambda equals 0, which is dxw bar, is simple and principal if and only if w bar is monotone. See, if it is monotone, and we know it's outside the essential spectrum by we computed that. If it is monotone, then it's the principal eigenvalue. 0 is the principal eigenvalue. There are no other eigenvalues with real part 0, and the wave is stable. If it's not monotone, it's not the principal eigenvalue function, and there's another one that's larger. But that would have real part bigger than 0. No good. We also know it's real. And so we know a lot in second order scalar case. So actually, I kind of portrayed it as the Lyapunov theorem that says if one has spectral stability, then one gets nonlinear stability, because that's kind of my aim for general systems. But in this case, it's a complete result. I mean, Salinger completely solved the problem. Now, for viscous shock waves, well, they're monotone because they solve a scalar ODE. But that was because of conservation. That's because we were able to integrate once the equation was a perfect derivative. In general, it would be a planar ODE, for example, for reaction diffusion equations, and there can be examples. So reaction diffusion with a bistable potential gives, sometimes it gives connecting orbits from two heteroclinic saddles. Sometimes it gives periodic solutions. Sometimes it gives homoclinic solutions. So a solitary wave type solution. That solution is unstable. And there are also traveling fronts, which are monotone, and those are stable. So one gets really a lot of fun information about those problems, all from this Salinger theory. Okay, that's aside from our main goal here, but I think that it's quite interesting to mention. Okay, hope that's clear. Okay, now we're coming back to what we were doing at the end of the last lecture was instead of using weighted norms, we want to use diffusive stability, so properties of diffusion. And to understand that, we look at the constant coefficient case, by which I mean the linear part is constant coefficient, but I'm allowing a nonlinear term of the type that we have in the shockwave case, which would be stability of a constant solution for the scalar conservation law. And what we know is the linear part, it has an exact solution with the green heat kernel, which I'm writing as g of x minus yt. Here's the formula, the heat kernel formula. And all I really need is the LP norms of the heat kernel. And they have a nice formula, which one can get just by the scaling laws, the scaling invariance, that everything depends on x minus y minus at over t. That's, one can change variables and compute this, and you get a certain power of t outside, and then you get an integral non-involving t. That's it. So that's where we were at the end. Okay, so lemma A, e to the LT naught in L2 is less than or equal to a constant times 1 plus t to the minus 1/4 V naught L1 intersect L2, and B e to the L dx. All right, like e to the LT dx of V naught, which, by the way, is equal to dx e to the LT V naught because it's constant coefficient. The derivatives pass through. L2 is less than or equal to a constant 1 plus t to the minus 3/4 V naught L1 intersect H1. So these are going to these are replacing the exponential bounds we had in other cases. They're not. Okay, it's not nearly as good as exponential, but we'll see that it's just good enough. And then, okay, so yes. N is it would just be like L. Oh yeah, that's the constant coefficient one. Yeah, right. Yeah, the left-hand side of the above with a constant. And yeah. Okay, so the proofs are not difficult. We use yeah, is it yeah, I guess it's Young's convolution inequalities. And we have that G convolved with V naught in L2 is less than or equal to the L1 norm of G times the V2 L2 norm of V naught. And that's the easy one. It's just triangle inequality. Basically, I'm putting
if you compute more derivative, do you gain more?
Yes, you gain one t to the minus 1/2 decay for each derivative, right? And right. I forgot to say. I meant to say this: dx to the kg in LP is like a constant times t to the minus 1/2 1 minus 1 over p minus k over 2. I meant to, it's in my notes, I didn't write it, that we need that, which also comes from scaling. You get more, you get a lot of different terms as you differentiate, but each of them fits well with, they all have the same scaling laws. Yeah, I need that for the next one. But this one, let's just to see it, this is g of x minus y t v naught of y dy. And I can write that as g of z, let's see, v naught of x minus y, g of yt dy. And now I'll put the L2 norm in x, that's in x, on v naught, and use triangle inequality. So I'll put x here. It's not a good notation, but this would be less than or equal to the integral of v naught of x, sorry, of I'll pull v naught out with the L2 norm, and then I'm left with g of y t dy. And this is L1 of g. So that one, I don't even need Young's inequality. I just need triangle inequality. And actually, that's all I need for all the estimates I'm doing right now for both. Because I'm going to either, I'm always going to put L1 on one of the terms and L2 on the other. That's all I'm going to do. Okay, so okay, so this one, okay, so this is less than or equal to a constant times v naught L2. And here I'm going, that takes care of t less than or equal to 1. For t less than or equal to 1, I just want 1 here. I just want bounded by c times v naught in L1. So I just got that. And then if I want p bigger than or equal to 1, I take g convolved with v naught. L2 is less than or equal to, now I'll reverse it. And p is here 2. And then I have v naught L1. Well, this is my 1/4. Yeah. So that takes care of, now I've taken care of the first claim. And the second claim, well, it works exactly the same. There's one more t to the minus 1/2 in all the estimates. And that's all I claimed. Instead of minus 1/4, I claim t to the minus 3/4. Oh, and there is one detail. Why do I have H1 now instead of L2? Well, I still have this. I have this for t less than or equal to 1. It's not bounded. It still has a t to the minus 1/2 singularity that I don't want. So I put the derivative onto V naught. So I'm being very, very careless. I'm doing only the easiest things. Okay, so that's proved. Okay, so now, again, the comment, we're getting decay from localization plus diffusion. So these are estimates that go from low norms to high norms, and we can suddenly have decay, whereas the Helios-Theta theorem says we could never have decay from L1 to L1 or from L2 to L2. We can't have a uniform decay rate. No, at least not. It can be at most bounded. Okay, so now we'll do a nonlinear stability argument. Let's see if I can. Okay, so, and what are we showing? Stability of the constant solution. W of x t is identically equal to W naught equals constant. That's the problem we're solving here, which is an interesting problem by itself. So we have dt v minus LV equals dx n of v. I've just rewritten the top equation in an abstract form, and here n of v is O of v squared for v bounded.
Yes.
Sorry?
That is what was this?
No. This is time asymptotic stability. So I'm going to show it decays to if any perturbation will decay to 0. Yeah, as time goes to infinity. Well, Posinus says, well, the most it says is that I have a nice the solution stays bounded up to some short time. So there's quite a difference between those two.
Let's say evolution problem, I still decay for the solution. T goes to 0, which is for the population. Then the same thing.
No, as t goes to infinity is what I want. I want decay to 0 for a sufficiently small initial perturbation.
Maybe for W 0.0, then it's one process.
Let's see. Are you saying if W let's see. Oh, I see what you're saying. But I still will say it's not well Posinus. For W equals 0, W not equals 0, it's still no, it's still something else because it could grow. Yeah, so I'm going to make a distinction. Having global in time boundedness, that's much stronger than short time boundedness. Short time boundedness allows exponential growth, and so it's more that we're trying to get here. Okay, so So we are going to prove proposition for V naught L1 intersect HS sufficiently small. And I just think I need S equals 1 and S large enough. I'm going to have V at time t in L2 intersect HS is less than or equal to a constant 1 plus t to the minus 1/4 V naught L1 intersect HS. So with smooth enough data, N must be smooth as well. I need it smooth enough to S plus 1 or something, CS plus 1. But let's just take it to be Z infinity, because I don't want that to interfere with the rest. Okay. Okay, so we'll prove this by so proof. We'll set alpha of t to be the supremum. We're going to prove a bootstrap type estimate. Supremum 0 less than or equal to S less than or equal to t of V of S HS. Why did I write this? I just mean HS times 1 plus t to the positive 1/4, or 1 plus S to the positive 1/4. If I show alpha is bounded, what I'm trying to show is that alpha of t is less than or equal to a big constant times V naught in L1 intersect HS. Too many S's again. Okay, yes. I've got to decide which. I think the one that's going to bother me less is let's say HK. Are there K's? I don't have K's, do I? Or HR. HR. I think I'm safe. Yes, too many. Yeah. HR. R plus 1. Everywhere there's this would be easy in tech. Okay, I think that's good there. And now putting it back, this is R. HR. There. This is what I want to show. If I show this, I'm done by definition, because what I'm trying to show, then I would have that alpha, that the HR norm would be bounded by 1 plus t to the minus 1/4 times alpha of t. And if alpha of t is bounded by a constant times the initial data, well, that's my proposition. So that's what I'm trying to show. And the claim is for VHR sufficiently small on 0 t, we have alpha of t is less than or equal to a large constant times V naught L1 intersect HR plus alpha of t squared. So the usual same bootstrap estimate we've been doing.
not get the view is getting.
No, I haven't. Yes. What have I done here? Okay. I'm going to say without loss of generality, V naught, W naught equals 0. Yeah, yeah. Yeah, say V equals W minus W naught. That's really what I want. And this is what I want to show. Yeah, yes. I'm sorry, I left out the yeah. No, thank you. That's yeah, of course I need that. Right. Okay. Now, okay, so I need to prove this. Okay. So I'm going to prove the claim, and then that will pretty much do it. So we have V of t is e to the LT V naught plus integral 0 to t of e to the LT minus s dx n of v at s ds. And so this gives us, using our estimates, that V of s is less than or equal to, and here I want L2, is less than or equal to a constant times 1 plus s to the minus 1/4 V naught L1 intersect L2. That was one of the first estimates. Okay, and then plus integral from 0 to s, 1 plus s minus tau to the minus 3/4 times v squared L1 of tau. Oh, sorry, v, this is L1 intersect H1 of tau d tau. And now, so that's a big constant times there's, I'll take big constant times 1 plus s to the minus 1/4. And now I have V naught L1 intersect L2. It's actually better than I need. And then plus, okay, alpha of t squared, because now I'm going to bound this by either, sorry, I'm going to bound this by, the L1 is the worst. That's the L2 norm squared. But I could also do the L2 norm. I'll still have a double power of alpha. 0 to, no, I want S. I'm going to do S because S is between 0 and t, and I'm finally becoming more strategic. It doesn't look the same because earlier it wasn't optimal. And here I'll get integral of 1 plus s minus tau to the minus 3/4. And this will then be 1 plus, well, okay. Yeah, I'm actually, yeah, 1 plus s to the minus 1/2. 1 plus tau d tau. Well, alpha of s, but alpha of t is bigger than, yeah, so for 0 less than or equal to s less than or equal to t, and I'm going to use alpha of t because I want to, in the end, it just makes it easier. And now this is bounded, this is convergent. Let's see. Oh, I'm sorry. If I pull that out, then I have to put in 1 plus s to the positive 1/4. And this is 0 to s. And this is going to give me a s to the minus 1/4. Both, what you need to check is that both pieces are convergent by themselves near the singular, like near the bottom and near the top. Because if this were bigger than one, that would, let's see, no, it's actually, since I have ones in here, it's not a problem. But the algebra might not work out. Then I just add these two and subtract one. So 3/4 and a half is 1 1/4. Subtract one, that's a quarter. Balances with this.
Did you factorize 1 plus s to the minus 1/4?
Oh, I know that I have, okay, I have this. So I pulled it outside.
Yeah,
And the other one, I put a balancing term here. Yeah. I put a balancing term here, which exactly cancels this one. Sorry, it's actually 1 plus s because I have one everywhere it's 1 plus.
yeah.
And so these cancel. And now I'm left. This is just bounded. Oh, that's an alpha of t squared. It comes in as a square because of the way that, because I have v squared here. And I'm, estimating v by alpha times something else. Okay, but that's what I wanted to show. That's my bootstrap estimate. That's done. And now, now it goes as with every other argument that we did. It wasn't important what the decay rate was. The only important thing was the form of this bootstrap argument and having a nice, well-posedness, short time existence theory, so that this is continuous. These norms. And then I find that for as we did before,
And the same argument applies for higher order derivative.
well, I'm not quite. I'm not done right yet. You're right, because I have to do the higher derivative.
Sorry, can I interrupt for just a sec? We lost the board and sound.
Audio is off and video is off. I think we're about to do better. Can you see now? It just shifted. I think it's okay. Can you see now?
Yeah, we can see now and hear.
Somehow,
Yeah.
how long have you been blind? And
Just like a minute and a half. Not
oh
long.
boy. Okay, I've got to check the chats more often. Ah, I see. Probably says something like, we can't see. Okay, so tell me at which point in the argument stop. Did you get the proof of the claim?
We just finished the proof of the claim, like the end of that board on the right, but then we missed what happened after that.
Oh, okay. So the question was, what about higher derivatives? And the answer is, oh yeah, we have to do higher derivatives because, right, it's not only L2, it includes HR actually. This should be HR, this should be HR, and this should be L2. Because in the nonlinear damping, and there should be a constant, the nonlinear damping slaves the HR norm to the L2 norm. That energy estimate that we proved, even for the variable coefficient case, also works here. And this was the energy estimate. Yeah, well, yeah, by this, yeah, by the dissipation of high derivatives. Yeah. And so here, okay, so now what I'm doing, I wrote, this is nonlinear damping, which we've proved before. And so I'm going to just use it here, unchanged. And the first term is exponentially decaying, so I just put order of e to the minus 2 theta t. It's harmless. It's the next term that matters. I'll pull out a c times, okay, now I use alpha squared times 1 plus s to the minus 1/2, because that's minus 1/4 squared. Now I'm just using the definition of alpha, but now I've proved that this, yeah.
Confused by so assume n is 0. So you have only the linear.
Oh, n is 0. Yeah. Okay.
Yeah. And so you're claiming that you have a exponential bound, right?
Yeah.
And so why we don't use this instead of the algebraic one?
Because at r equals 0, you have a problem. At r equals 0, it's not it only slaves higher derivatives to L2. It slaves, it's true, it slaves it to L2. Well, it's still true, but it only gives information in derivatives of V. Yeah, so I guess it gives exponential decay of dxV, sort of.
Okay.
In many derivatives, but not of V. Because when I set R equals 0, I just have the L2 norm is bounded by, okay, some exponential decay times L2 plus basically a memory. It just says the L2 is bounded by L2. And it's worse because I put a constant in there that is arbitrary. So it doesn't tell me anything.
Okay.
Yeah. No, I think about that a lot sometimes. This is a funny point. I agree.
With or without the A, this did not matter.
Yeah, well, with or without the A, with a variable coefficient or constant. Now we're just doing heat equation with nonlinear term, but we could have done with really arbitrary convection. That lower order term didn't matter for our energy estimate. Those were all, we could have almost crossed that term out. It gives nothing bad.
Does not contain derivative. It's only B squared.
Well, it does have a derivative in front of the V squared, but just, yeah, that is important. Yeah, otherwise, then that could affect, that's a diffusion now. Now it's a nonlinear diffusion, and maybe I could handle it, maybe I couldn't. I would need more information, I think. I guess, well, let's see. Actually, you know what? That wouldn't hurt me too much, as long as I know that U is small, I could absorb it. I could just give up more derivatives in my estimates. I don't really care. I would work in H2. Yeah. And for the nonlinearity, I could have two derivatives. It would be okay. Yeah. But even though I'm doing this for a semi-linear scalar case, these arguments work for the quasi-linear, partially parabolic case. They work for the real viscosity because I've been careful not to do things that wouldn't work in the other case. It's not at all obvious that I could get such an estimate with physical viscosity. That's what Matsumura and Nishida did, and this was fantastic. And what Kawashima formalized into some famous estimates. But so it's not easy, but you can still do it, and it's known that these tools are available.
What are the name of the people?
Matsumura and Nishida. Let's see, already here. I think that's like 83. And then I'm going to say Kawashima and Shizuta separately and together, and many. Okay, there are several. There's a book of Kawashima containing his thesis, and it does this kind of thing. It sort of subsumed a lot of a variety of examples of this in the literature. He showed exactly what is the algebraic structure you need to do this and get such bounds. So, but yeah, it's some of the things I'm not saying are much more interesting than the things I'm saying. Those are big results. But okay, now back to our semi-linear and scalar case. So at this point, I'm actually done because now I put in that I know alpha of t is bounded by a constant times v naught h1 intersect L1 plus alpha of t squared. And that is now what I want because, and this, what does this give me? This is an exponential decay against algebraic decay. It basically gives me this algebraic decay, but evaluated at the top end. So that's 1 plus t to the minus 1/2. And this was still v naught hr. Oh, this is hr. Okay, now I take the square root and I'm done. Now I really am done because that now gives me the HR estimate that I wanted. I really only needed to get L2 because by this sort of memory kernel effect, whatever I put in here, I'll get back in this term. Whatever estimate I get on L2, I'll get that estimate on HR using this kind of estimate, unless, and we saw this in an unfortunate example, unless this is actually decaying faster than this, then I'm not going to get, then I get back the slower of the two. So that's what went wrong in an earlier lecture. But here, no problem. Algebraic is slower than exponential for any exponential. So that's what I get back. Okay, so now that's the proof of the claim. But once I have the claim, then I get the result. And I can say, well, I could say more about exactly how big the things have to be. We did that in other examples, but we know if V naught is small enough. Let's see. This is what we have, because we only needed to show that alpha remains smaller than this, but we'll show. But the claim implies that alpha of t is less than or equal to twice c v naught L1 intersect HR if v naught L1 intersects HR is sufficiently small. And you can plug things in and see exactly how small it has to be to work. But basically, it's going to tell us that if we ever reach this bound, we're actually much smaller. So we can never reach it. So now all the pieces work the same as in the exponential decaying case, and it's very nice. I think this is a very nice argument. It's not, it's an old argument, but it's a good one. This is the basis of these. I've mentioned this before. This result by Matsumura and Nishida showed for compressible Navier-Stokes, singularities don't form for small HR perturbations now of the constant state. Whereas Fritz-John showed for the inviscid equations for compactly supported CR data R as big as you like, singularities do form in finite time. So that's very, very different. And it's not obvious because it's not fully parabolic. So there are hyperbolic parts. The mass is not smooth in compressible Navier-Stokes. So a priori, it's not clear that this wouldn't form a singularity as for conservation laws. But actually, such an energy estimate prevents that. But that's not all they did. They basically did a version of this argument I just showed you for full system, three variable system, which is compressible Navier-Stokes. And they did it's more than that because they did it in multi-D as well.
Professor Zumbrun,
Yes.
we are seeing the left two boards instead of the right two boards. Ah, yes, thank you.
Okay.
Given what you told us now, would it be extendable to higher dimension?
Let's see. Yes, it is under some assumptions that are mild. So what is it that we need? We need estimates on the linear solution operator. And okay, so it's a Fourier transform. Expand everything in small frequencies. That's governing the time asymptotic decay. And if you can extract this same kind of well, there wasn't really any structure here. It was just a heat kernel. But if you can see if all of the modes, let me put it precisely. You have a symbol. Okay, now K is in RD. V hat of IK. T is the Fourier transform. You have S of IK is now equal to negative AIK minus IK1 minus B IK2 minus K squared. Minus K squared, and you want the dispersion relation, so lambda of IK, which are in the spectra of S of IK, should satisfy real part of lambda of IK is less than or equal to a negative constant times k squared over 1 plus k squared. That's the sometimes called the dissipativity condition. And this is, here K is the Fourier transform. It's now d-dimensional since we're in multi-d. And this is a constant coefficient problem, so we can attack it by Fourier transform. And this is what you need. Okay, well, how to show that? But for 1D, this was pretty easy because we just, without loss of generality, took A to be diagonal. There is no B. We can expand things pretty easily. But so, for example, I would recommend maybe looking at Kawashima papers. And there is a genuine coupling plus symmetrizability. So without any diffusion, we would just need, I mean, not need, but we would be happy if we had like a Friedrich symmetrizable system. If we could simultaneously symmetrize A and B, that would give us optimal bounds, which are just boundedness. And now we have diffusion. Oh, I should have put, I'm sorry. I should have put in another. This should be a matrix, and this is possibly degenerate. That's for gas dynamics. It's degenerate. That's what's interesting. So even if it's not degenerate, though, you need for it to work nicely with these. And so there are conditions that make sure that they behave nicely together. But I say it's a very interesting topic. You can see it gets involved, and there are very beautiful answers. But that would be. I actually have some intention to look at this later on in the next module, but maybe not today. But only to indicate, yeah, there's something very interesting there. Okay, and okay, but I should mention also to do this, I used a very heavy piece of machinery that I actually know pointwise bounds on this green kernel, but I only proved HR bounds. It is possible to carry the pointwise description through and have a pointwise estimate on the solution, but it's becomes rather delicate. Even in 1D, it's not delicate. For the scalar case, it's not delicate. But for the system case, it's delicate because, I'll just draw a picture. Okay, suppose we have some compactly supported data. You know, roughly there should be waves going out that look like small convected heat kernels, but now in two different directions. So that's a good starting point. That's the linear behavior. No trouble there. We have that gives us pointwise control. But now remember that nonlinearly, these things are coupled. So this outgoing wave is sending signals off in the other direction through the nonlinear interactions. And what it means is there will be, it turns out, there will be an algebraically decaying sort of a bridge in between the two. And you need to get rather sharp bounds on that. So this is Liu and Zhang. They have an AMS memoir. I think it's around 2005, but Liu did a nice calculation very early on, much earlier than that, I think 90s or late 80s. the key estimate. How uh, the point is that you have to use the transversality of these signals, that they don't intersect for very long because they're moving in different directions. It's subtle. Okay, so those are some of the things that might go into a pointwise description, and that's just for the constant perturbations of constant solutions. If you want to do it for shocks, it becomes even more complicated. So for that reason, it would be nice to have a way not to do it. That I'm showing you that way. But you can also use these same techniques to do it, but you have to do things. You have to use some of their techniques blended with this. Okay, let's see where we're doing 56. Okay, I think that is the perfect place to stop. So let's take a 4-minute break. I'm sorry for people in the audience. I guess I have to check the chat to make sure this doesn't turn itself off. You can hear me now, correct? Okay, and see. All right.
The chat there.
Yeah, that's all good now. Perfect. I need to check a bit more. I need to wander over there more often. Oh, okay.
Yeah, that's fine. That's what I'm saying. Yeah, let's say yeah. That would. Yeah. Yeah. Maybe if I have to start. Yeah.
Maybe we can just round the thing.
Yeah, you can choose that movie. Can I pass it on? Well, I'm also sorry, like, I have to talk outside like this. First, talk about when to see.
Okay, so it is.
Also when, because like he's reading, so I don't know if he's going to add. You see, I need to add some stuff, so.
Sorry.
No, it's only. It's a very long, difficult thing. I just hope that everything will be well. Antenna mode for finally 1 year.
like slow decay. We were trying to, the mass volume result on the 5.4.
So yeah, doing long time.
Yes, exactly. We're doing long time, but for by quantity, we're actually proving that the epsilon for time scale for mass volume is optimal, like with the requirement. So for quantity is already very rare. To get estimates are almost like geometry. Actually, I think it's
If it's optimal in terms of the decay of anything, no,
yeah, exactly.
but there could be a luxury.
Yes. Yeah, because you have 1 minus 1 half, which is cannot do that. That's the best. And this is why we're proven. But estimates comes with derivative in frequency, and that makes you lose almost like the 1 to 1 half. And this is the issue. And that's a different method from what Masmoudi and the other people did. But yet they cannot close they cannot really absolutely precise. And they also proving that little express again. So if epsilon beside
It is simplified, because they
Yeah.
proof is
Yeah.
very long, no?
Yeah, they have 240 pages. We did it in 75.
Okay, so
Yeah, so that's
maybe readable.
Yeah. Yeah, because there are people when I was trying to read, I was like, that's too much.
Yeah.
So
Oh, nice. Maybe it's not like it was, you should.
I should have.
Yeah.
Yeah.
I mean, really.
Oh, yeah. Yeah, I'm trying to do now the Schrodinger one on supercritical, but moving solid. That's
That's another project.
yeah, that's another
Okay.
which is
Future.
which yeah, it's going ongoing. Yeah.
Okay. Very kind, because I did RFA about solitary.
Yeah, with Bukani, it's in, yeah. But
With internal mode, but the other point of view, the energy.
yeah, oh, energy, yeah. Right.
So
Energy space is a bit, I think like, yeah, I don't know, maybe arguments are bigger, but I don't know the weighted norms I that involves. Because the tools
Yeah,
with
the tools,
I have an idea.
I mean, in the energy space, less technical, but
yeah, demanding.
I mean,
It's still demanding. Yes.
Yes.
It's not that easy.
Yeah, I have next one. If you had.
very short.
I'll help you see if you make sense there.
30 pages.
Yeah.
No.
But you need to have some like
It's a
right idea.
difference.
Yeah. Kind of different.
Oh.
I'm taking advantage of the break to work. Yeah, it's the best week of the semester for work.
Yeah, halfway.
That is summer. It's also
Okay, so now I've given the idea what we want to do. We want to substitute for the exponential bounds. Oh, wait, I should wait 1 second. Yeah, we're not all together yet. Wait 1 minute. Okay, everyone can hear me out there? Yeah, okay. Okay, well, maybe I'll just start. So motivated by the previous example, we were going to try to get pointwise bounds on the green kernel for our variable coefficient problem using the inverse Laplace transform representation. But what I find to be very instructive for that is let's do the constant coefficient case in that way. And it's actually, this was the key for me, this little computation to understanding what to do. But okay, so let's start with how do we get from this, the constant coefficient case, how do we get to g of x minus yt equals the well-known explicit formula. Okay, scale invariance reduces to an ODE solve. Right, just this is the quickest way. And so, for example, you can find that in Evans' grad PDE book. You can find it in Walter Strauss PDE book. I was just teaching, in fact, I taught this, but I also know that Walter Strauss' book also shows this other way, because it was in there somewhere, and I made a big deal out of it. So the other way is Fourier transform. And this one is pretty interesting. So we convert this, oh, there's a V there. Fourier transforming, dt v hat equals negative aik minus k squared v hat. V hat at 0 is v naught hat. So that's another way to convert to an ODE or a family of ODE. They're readily solvable, and we get v hat of t, ik, is e to the negative aik minus k squared t times v naught hat. So we have a solution formula, and we want to convert this to a green kernel. Okay, so okay, so first we use the inverse Fourier transform. Will tell us how to do this. This should be v of xt should be 1 over 2 pi. I think that's the right normalization. And then e to the ik, let's see, what do I want? E to the ik, x e to the minus, e to the minus ak minus k squared t dk. And there's a v naught hat. That's important. Okay, so now, first observation. The convolution theorem says if I take the inverse Fourier transform of a product, that's equal to the convolution of their inverse transforms. So that will be 1 over 2 pi I e to the ik x minus y e to the minus ak minus k squared t dk integral against, well, this inverse transform is just v naught of y. Yeah, this is just the transform of v naught, so its inverse transform is v naught. And so this is now a convolution. So this will just define, this is g of x minus y t. That is the green kernel, but we need to estimate it. Okay, so you just take, you combine these, and let's see if I can do it very nicely. So combining these, we have the argument of the exponent is ik x minus y minus at minus k squared t, and we'll write that as x minus y minus at over 2 square root of t plus ik square root of t squared. I'm just completing the square. So, okay. And, all right, so this involves no k's. This can come outside of the integral. This e to the minus x minus y minus at squared over 4t. That's great. I got my term. And then, you know, the rest, what do I do with this? Well, I want to do substitution, basically. But it's worth noticing exactly what I'm doing when I do that. So yeah, I basically want to show that that's a constant and bounded. Well, a constant times some factor of t, which is t to the minus 1/2. So I have e to the minus x minus y minus at squared over 4t, and then times the integral e to the minus, oh, let's see what I do. Oh, e to the, there's a minus. What happened here? Yeah, I think I just left out a minus there. I hope that's what I did. No. Ooh. Oh, no, that's correct. Yeah. I need to factor out the I squared. So now I'll have k squared of t plus x minus y minus at over 2 square root of t. And I have an I guess, here, squared. And what I will do is I'll take this to be z over, this to be z square root of t, which means I'm taking k to z, k to k plus x minus y minus at over 2t, and there's a minus, times I. I'm taking that to be z. So what am I?
No. Professor Zumbrun, we lost the board again. And sound.
It keeps, okay, somehow the video and sound are turning off. You have it now?
Yes, we do. Thank you.
You have the correct boards.
Yes.
Okay. All right. So where did you lose the sound? We have this formula. We want to do a substitution basically, but to do that, we need to move into the complex plane. So what this really is a Cauchy theorem computation, and we're moving the contour. and showing that we have sufficient decay at infinity to do so, but that's pretty clear from this type of double exponential. And once we do that, what we get is we get another Gaussian, and it's real. And we know that this is, I guess this is 1 over pi t, the t square root of pi t, the t by scaling, and the 1 over square root of pi is by this trick of going to polar coordinates, right? You go to do a two-dimensional integral and then take the square root, and that one's integrable. So it's a bunch of calculus, but anyway, and so that's how we get the 1 over square root of, and I left out, there was a 4 here somehow. Why was there a 4? I'm not sure. I lost the constants, but for some reason it's 1 over square root of 4 pi t. Oh, no, it's square root of pi t. I was right. There's a 1/2 out in front. So that was okay. There's a 1 over, no, there was a 1/2 out in front. Yeah. Okay. If we do it carefully, we get the right constants. But this is the key point. The inverse Fourier transform of a Gaussian is a Gaussian. That's basically what's going on here. And why? Well, yeah. And how do we rigorously do this? By moving a contour. So we're changing from spectral information to spatiotemporal information. And this is the essence, I would say, of complex stationary phase estimates. Well, I don't know if that's just my terminology or someone else's, but I want to distinguish from the usual stationary phase where you integrate by parts and you get powers of t or x or something. You get algebraic decay, but if you really use this kind of moving of contours, then you have some nice Paley-Wiener type estimates. That's what this basically is. And you get the exponential decay that's really there if you have the complex, if it's analytic. So you get much more. Okay, so that's most of it for complex analysis. Maybe I want to point out, though, alpha I don't always go one way, right? Alpha is x minus y minus at over 2t. And the center, so that's a moving heat kernel, moving with speed a, and at the center, alpha equals 0. But if we move to the right, well, we've got to move positive alpha. But if we go to the left, the correct thing is negative alpha. So this is not, it's not exactly like one fixed contour. It's microscopic in a way, or local. We're looking for each x, y, and t. We take a different contour. So and we're going to have to do something much like that. Okay, so now Laplace transform. Okay, that's so the Fourier transform that was in the Strauss's senior or junior or senior undergrad book, but this one you usually don't see. Okay, but let's see. So we have e to the lt is this principal value integral of e to the lambda t, lambda minus L inverse v naught d lambda. Okay, so and the resolvent equation, let's see, is lambda minus, well, it's a lambda plus a dxv minus dx squared v equals f. That's the resolvent equation. And so we need to invert this and, well, actually we need v naught over here. That's what we want to solve. It's really with a check. Yeah. But this is e to the LT v naught. Okay, this is the inverse. No, everything's okay. This is actually v naught. That's the initial data that goes there. There are no checks here. But this is a check. That's true. Right. Yeah, and that's what v check is. This whole piece. Okay, so, but now I'm going to follow the approach that I did before. We're going to write it as a first order system. V check dx, v check dx is equal to, or sorry, minus 0, 1 lambda a dx v check dx v check is 0, and negative v naught I think should go here. So this is what I'll call v, this is a, this is v, and this is f. So that's how you do it. And then when we look for the eigenvalues, mu of lambda of A, which is it's a matrix depending only on lambda, they solve the indicial equation, which is lambda plus A mu minus mu squared equals 0, or lambda equals A plus or minus square root of A squared plus 4 lambda over 2. And here I'm going to take A positive as before. So there are two branches. So there's mu plus, which is has real part strictly positive, and mu minus, that's where I take the minus sign here, and this is neutral mode, and it's negative, real part is less than 0 on omega. And what is omega? That's the set of consistent splitting. So this, I'm going to call this gamma, lambda. Capital lambda is the dispersion curve. And omega is everything out here. Everything to the right of this essential spectrum boundary. And the real part, so here we have, so everywhere to the left of the imaginary axis, we have real part of mu plus is positive. And here we have real part of mu minus is less than 0 out here, and it changes sign. If we move across the boundary, it changes sign. So over on this side, real part of mu minus is less than 0 as well. And on this side, real part of mu minus is less than 0. Okay, and that's all we need to know. Okay, and the solution by variation of constants or this the Lyapunov-Perron is integral from minus infinity to x, e to the a, x minus y, pi s, which is associated with mu minus. That's the stable mode. That's the real part less than 0. V naught of y dy. Okay, and it's actually, it looks like it's 0 V naught. That's how it looks, because that's how F or negative V naught. And then minus integral from x to plus infinity, e to the a, x minus y, pi unstable, V naught of y dy.
This is the. Oh. The Quran V XV.
Yes, yeah, right. So it's interesting that it gives us information at once on both v and its first derivative, though we're going to throw out the information on the first derivative for the most part. And then, but the data comes in only in one. It doesn't come in with a derivative. It comes in here, no derivative. And this is analytic on omega closure. So why is it analytic? Well, because even though even in omega bar, okay, where was omega is here. This is the consistent splitting set. I'm saying it's analytic even across the essential spectrum. And that's because the spectral decomposition is it still makes sense. It's perfectly well defined. I left out one thing. This is where, so where do I lose analyticity? Only where lambda is negative a squared over 4. That's the branch point for those eigenvalues. That's where they collide. Everywhere else, it's analytic. And look, this is lying inside the essential spectrum. It's not at the boundary. So we can go quite a ways into the essential spectrum. We're still analytic. That's important. Okay, but there's another solution operator, and that would be, what if I look over here? I'll call this omega tilde, like a complement of the consistent splitting. Over there, so it's analytic. Let's see. So this is in omega, and in omega tilde, I would just, now everything's stable. So it's just integral from minus infinity to x of e to the a x minus y, 0 negative v naught of y dy. This is analytic on C1, on the whole complex plane. It's just not correct. It's not the correct solution operator that belongs out here, that is associated with the resolvent. But it is perfectly nice. So what could I do? Well, what I could do is this. What I will do, I start with a contour here. So this is my initial contour for the inverse Laplace transform. I'll move it all the way across. In fact, I can move it, if I'm careful, I'll see, I can actually move it out here. I can move it along an arc. And because of the rapid decay, I can actually make this equality. That's not obvious, but I can. And what happens to this? Well, now what I'm going to do is actually, I'm going to notice, well, what happened? There's something happened at the boundary. There's a jump. So it's like when you cross a pole, you get a residue. If I cross a boundary like this, I get a jump. Kind of reminds me of Hilbert transform or something. So I'll get the integral over lambda, the dispersion curve, of e to the lambda t, lambda minus L, or I'll say jump in lambda minus L inverse v naught d lambda. And I should have all along been There was a 1/2 pi I that I left out of everything, but belongs there in the principal value. And then plus something over here. But look back here. This is stable. This is exponentially decaying. This is uniformly bounded everywhere. Oh. What happened here? Right. So when I put it in, I've got an e to the lambda t, which is negative. This is exponentially decaying, but there's no boundary here. I can push this all the way to negative infinity. This is actually zero. This quantity is zero. This is less than or equal to e to the minus gamma max t times a constant times phi naught. What I'm doing is I'm trying to calculate the inverse Laplace transform, and I'm doing it by I start with the transform in the format A, because that's the correct one. I'll move it across this boundary, and when I go across, I'll accept the jump and change to part B. And part B is well defined everywhere, and I can push it all the way to negative infinity. It only gets better. It has an e to the lambda t in front, and everything else is bounded. So what I'm left with is just this. I have an integral. Yes. So this is v of. So this is v dx v of t is equal to integral now on this lambda, this dispersion curve of e to the lambda t, and then okay, so now, but I have to. What is the jump between these two representations? So one of them isn't present in both, which is the let's see, well, what I have here is a stable guy from minus infinity to x, unstable from x to infinity, and then that flips. We're now going to consider the unstable guy becomes a stable guy when we go across, and it's now included in here. So the difference is just what was originally the stable guy. So it's just going to be e, let's see, e to the lambda t, e to the mu minus of lambda, x minus y. And I'm now integrating, this from minus infinity to infinity. And that's what I have. This is mu minus of lambda times x minus y, because that's the component, and there's a projector in here. Of lambda that I've left out. It's going to somehow convert us back because, okay, so that's what I have. And why is this interesting? It is interesting because remember now the relation between the dispersion relation and these spatial eigenvalues mu. Specifically, recall on the dispersion relation, that's exactly where real part of mu minus of lambda equals 0, i.e., mu minus of lambda equals ik of lambda. So this and where and lambda equals negative ik of lambda minus k of lambda squared. there's a transformation from mu to k. And if I make that transformation, this suddenly looks like, so v of t will be the integral over gamma of e to the lambda minus of k of ik times t, and e to the, okay, so what is mu? Mu is ik, x minus y. And then we have d lambda over dk, we have a pi minus, and we have dk. And we also have, and inside we have integral minus infinity to plus infinity, v naught of y dy. Now k, yeah, k is real. Because that is the defining relation for, I mean, it's one relation for, it's one definition for lambda, the curve lambda. It's the places where the spatial eigenvalues are pure imaginary, or it's just a dispersion curve, looking from the Fourier point of view. And so, and there's a d lambda. So if we reverse the order, that's equal to the integral of e to the lambda of ik t, e to the ik x minus y, dk. And then something, so keeping only the first component now, up to now I kept v and dxv, but I only want v, so now it'll be just a scalar quantity, and so I can forget. Notice that the forcing came in the form 0 v naught, so that's scalar. It's not it's not vector. After I undo all the coordinate changes, this has to be the green kernel. This is a kernel. X t y, or x minus y t. That is a kernel, and it's integrating. I'm integrating it against v naught of y. It has to be the same as the Fourier one, and we can see most of it. We can see. Oh, sorry. Go on, Catherine.
The last line, what happened?
So okay, so we have to compute d lambda over dk. Oh, that's d lambda over dk. So we have to invert. That's an implicit function computation from this. And when we do that, we find that it exactly undoes the coordinate transformation, the projection, and just reduces to d by dk. By integral dk. Amazingly, all this collapses to just dk. This becomes just one. And so we're left with exactly the Fourier transform.
Miraculous.
It is miraculous. You know, it has to happen, but seeing how, if you go through every detail, it's kind of fun to see how it all works out. And it's not easy, is it? It's not obvious, I don't think, at all. You have to do this jump across here. And by the way, I think that's a very good trick, or not trick, but it's a good thing to keep in mind, that it's like a pole. What happens if you have a curve measure instead of a point measure in your result? Yeah. Lambda of ik, where lambda is the dispersion relation, This is lambda of ik. It's exactly what goes into the Fourier transform formula by solving the ODE. You do the opposite things. You solve the ODE in time and you get this, and this you get for free in Fourier transform. In Laplace transform, you get the e to the lambda t for free, and you have to solve for the mu.
And then K of lambda, it's the same K?
Yes, yeah, it's the same K. Yeah. So I'm basically going to switch from this is a yeah. So I'm parameterizing the curve capital lambda by K because that's going to I know it has to be that, right? It has to relate back to Fourier transform. So I parameterize it by K. I do a substitution to integrate in K instead of lambda, which really means, say, the imaginary part of lambda or something. You know, it's contour integral. And what I find is miraculously, all the complex stuff disappears. I'm left with a real integral, which is exactly the inverse Fourier transform. But to get there, I had to do all these steps, and it's kind of cumbersome. There's another point, maybe that, yeah, I used that it was non-characteristic. That was used very heavily because, where's my first? This picture, this branch point is at negative a squared over 2. If a is non-zero, that is off the imaginary axis. And I used that heavily to do this because I needed to get across the essential spectrum. Once I do that, I have something that doesn't care about singularities because everything is it's just written in a a conglomerate form, just integral of a exponential of a matrix. I'm not trying to separate into modes anymore. But if it were at 0, I would have a problem. So that's interesting. Where else? Yeah, of course, for the variable coefficient problem, we use it constantly. We used it from the very start to get exponential decay of profiles. And if we didn't have that, we couldn't reduce to a constant coefficient case at all. We couldn't apply the conjugation lemma. So we're using it even here.
Because later when A is non-constant relation, you cannot use Fourier transform, and that will be your...
Right, I can't use Fourier transform, but I like the Fourier transform. I wish I could use the Fourier transform. Yeah, so I'm going to convert it to this one. I'm going to do the same kind of tricks.
Justify by going from the Laplace transform to the Fourier. But in any case, we would not have a decay, right? In this case.
Right. From L2 to L2 or something. Right. We don't have decay. We can get algebraic decay between different norms, as we saw, but no, not from one norm to another. We're not going to get it. Yeah. So I want to say one more thing about this, and this is the thing that was, well, all of this was very instructive to do. I did this calculation over and over to try to understand what to do. And then the really informative one was, then I thought, okay, if I really want to estimate things, I have to move this contour. What is this contour? This contour is real part of mu equals constant. I'm sorry, did I say that right? No. Imagine, yeah, real part of mu equals constant because I'm pushing ik, I'm transporting it by a real. That's the same as shifting k by an imaginary. I'm really shifting ik by a real. This curve I drew over and over, this gamma, that's where things are pure, where mu is pure imaginary. And if I shift that by a real, okay, what will I get? So I'll get, instead of, so I know now that I've identified the two, I know that it must be another Fourier integral, right? The Fourier integral must be, the shifted one must be on the other curve. So here's gamma, and that's real part of mu equals 0. But now I can take gamma alpha, real part of mu equals alpha. And that's here. And that one will exactly give me the Fourier transform with the shift, which is the one that explicitly gives me the sharp bound. That's what I move for each x, y, and t. Gives me 1 alpha, which was x minus y minus at over t, or 2t, that was alpha. And I want to move to a different curve to get the estimate. And it so happens that that's actually an equality. It's not just a bound. But I did not use equality. I could have just taken moduli inside those integrals. I didn't need to know very much. With that, that's good, because I'm going to have some error terms. I have variable coefficients. I have powers of lambda all over the place. I need something flexible. So I need to move here. Yeah.
You said the real mu equals 0, but in the other pictures, there's real lambda equals 0, and real mu was
Did I write real of lambda? I didn't mean to say that. It's real part of mu is 0. The parabolic curve is real part equals mu, real part of mu equals 0. Yeah. Right. And if I want to look at what is the the spectrum of the symbol of I times ik plus alpha is gamma alpha. That's, I take I shift k, I take the symbol, and I compute the dispersion relation. Where does it go? Well, I don't have to do this again. We did this before. This is what we did with weighted norms. So I already know what happens. I know that it shifts. I know that it's basically a shift to the right or left by I think it was alpha over a, wasn't it? Or no, alpha a. It was alpha times a plus order of alpha squared. So what do I care about this? I only care about one thing. I know where do I go? I know that sometimes I go to the right and sometimes I go to the left. And something that I didn't mention before, which was important to mention, is when I did this, when I did this trick, this is a little too smart. We don't want to be that smart or careful. What I could notice is, actually, I could have stopped, say, here, and just accepted that this gamma tilde part, that's exponentially small. It's of order e to the minus x minus y, absolute value, plus t. It's decaying it's negligible. It's a exponentially decaying term. So I could have thrown that away. And another way of saying that is I could have stopped here and not ever considered this omega. Oh, that was an omega tilde. I'm sorry. Never considered that. And this part that I could just throw away this part. That's also exponentially negligible. And now I have, well, a different thing. I have only one part. I have the integral from x to plus infinity and not the rest. But I know that that must be tiny. The rest is over here, and it's exponentially negligible. And you can verify that directly in the Fourier computation, that you only need things on one side to capture the essential behavior. The rest is, if you're willing to throw away exponentially small terms, which I am right away to avoid all this stuff. Not only that, I only need the part that's near 0. The rest decays very fast. So those two things, these three things are to remember. And this was the one that was crucial. You have to go into the essential spectrum sometimes. not just up to the boundary. So this is reminiscent of the, it's like the limiting absorption principle. And that's what I looked this up, 1878 or something. Let's see if I can find that. I like this reference. You can just look it up on Wikipedia, which is what I did. But I think that's Sommerfeld, 1870. And this is a question of how do you pick the correct resolvent up to the boundary of the essential spectrum? But at the time we did it, I had not seen anything going into the essential spectrum. I think things, maybe there were some in between 1870 and 1998, or quite possible. But anyway, that was a mental block for me to go, to go past the essential spectrum somehow. I and my collaborator, we felt that was a barrier you couldn't pass, but you can. The difference is we're not the resolvent. That's a global thing. This is not the resolvent. This is a resolvent kernel. It's local in X, Y, and T, and it gives us. It's like we get a little more precision. We're blowing up the whole picture. Weighted norms play no role here. They don't affect the kernel. The kernel is independent of any space. So it's got information, but it kind of, the steps we're taking remind me of weighted norms. It's like we choose a special one weighted norm for each X, Y, and T, and that gives us a good estimate. So, I mean, you can think about those things all day and come up with statements like that probably, but it's kind of fun to think about, I think. Okay, so that was, that's the big one. And so one of the reasons we thought we couldn't go in there past the essential spectrum was analyticity of the resolvent. But I sneaked that in. The conjugation lemma allows us to do all these things because it reduces to constant coefficient with an analytic coordinate change. So now we know it's quite possible. We're only limited by the behavior of the limiting constant coefficient things, and things like where are the branch points of the eigenvalues as, this kind of computation. So it reduces it to that. And the final thing is what we drew here, that we only need the part near the origin, and we don't need to do this jump, but we don't have to actually convert to a Fourier transform. We can get almost all the information just on this side of the curve. But I'm kind of contradicting myself a little bit because I'm saying I can get all the information, so why don't I just stop there? Well, I would, and I do when I know it's exactly that. But sometimes there are error terms, and those are the hard ones to compute because it's not an explicit Fourier transform. Now it's something with an error. Now I'm going to do the moving contours and get my errors for free. So that's why I have to go inside. But by a combination of the two, it becomes possible to do some, what to me look like tricky Laplace inverse transform computations. I just move them into what to me is more familiar, just this inverse transform of a Gaussian as a Gaussian. We have also sometimes, so in my papers with Masha, we just used a vertical integration line and did Laplace inverse transform, and we get something that has to be equal to the other one plus negligible terms. But it's actually, you have to massage it a bit to see it. So that's why I still I think that was more direct, but I still kind of like this method for the understanding it gives to directly relate to the Fourier transform. Okay, so.
Is it in the context? The approach with the Laplace transform?
Yeah, we could find the exact inverse. Yeah, it's actually, it's one line. You don't have to do any of this, but then it doesn't look exactly like a heat kernel because you can substitute x minus, here's y. X minus y minus at is approximately 2t for alpha small. And alpha small that's the important place. This is alpha is x minus y minus at over t. It's zero at the center of the wave. That's where the most important things are happening. Okay, so what can appear is take your heat kernel and anywhere you please substitute for t one of these. And you can make it look as strange as, so those are the kind of things that could come out of the Laplace inverse transform. And it's just a little harder to see, but you can see that they're equal, but there's one more computation. So you can take your pick, but I also like this picture of the jump because it tells you, how that, because that's the spectral resolution of this constant coefficient operator into sinusoids. And similarly, so for some periodic coefficient cases, we've actually used that to get at the spectral decomposition, spectral resolution for periodic operators. You could do the same sort of thing. And recently, Yanis Alexopoulos and Bjorn Durek did a very nice paper where they used exactly that. They used that and in all details to do very tricky computation, I would say. To get into they wanted to get into the L infinity stability. That's so you don't have a lot of tools that I'm using here. It's easier for Sobolev space. I have all these. I used energy estimates constantly to simplify my life. Nonlinear damping, but anyway. So yeah. Okay, that is that is all that I had to say today. And then on Thursday, we're going to do it for variable coefficients. I won't do all details for sure, but I'll show you how every term reduces to something very much like this. There are a lot of terms, though. That's why I'm not going to do all details. Okay, thanks. Any questions out there? See you. Still here? Yep. Okay.
Write the name of the three guys you just mentioned.
Oh, yeah.
Application.
Yeah. This is a nice paper. Okay. It's just two. And it is, I think it's Fitzhugh-Nagumo. And it's L infinity stability. This is not the title, but the title should have something like stability of Fitzhugh-Nagumo waves against L infinity perturbation. I think it's something like that. And yeah, a lot of innovations in that paper. These are periodic waves, stability of periodic waves. This is very recent. I think it's 2024. Yeah. This is the thesis of Yanis, who is a student of Bjorn. Very, very good thesis. Yeah. I think we have a good treatment of that. Yeah, that computation is in the first Zumbrun and Howard 1998 IU Math Journal. That's where we first did these pointwise bounds, and there is an introductory passage where we just do this computation in all details. Indiana University Math Journal, very famous journal. And, yeah, not to advertise. Or anything. Yeah, thanks for reminding me. I did mean to say that, yeah, because of course I left out lots of details here, but they're all in here. You can find them.
To read paper. I mean, I'm sure you have to read hundreds of times. Read them.
Yeah, and then I had to convince myself, yes, we really have to go inside the essential spectrum. Maybe we didn't, but we did it. There's probably a way around it.
Not get the math. You just cross this
Yes, yeah.
and then you take the sixth row.
Yeah.
Because this is where the talk of Jeremy was telling.
Yeah, this is 4 o'clock. Is that tomorrow or is that, yes, yeah. So I should come at 4. Okay. Very. Thank you. And that's the usual one. I went to it.
6,000, yeah, 60, 6083.
That's it, yeah. 10.